Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest. Find building where Alice and Bob can meet. The problem can be solved in different ways. In this video, I will be discussing about one particular way to solve the problem using segment trees. Segment tree is not at all a prerequisite for this video. You can still watch the entire video and it will still make sense, that I can assure. At the very end, we will be discussing about one follow-up problem as well, which will help you understand why segment tree is required in this problem and why and when can we avoid segment tree. If you are interested in specific sections of the video, all the timestamps are there in the description down below. You can move back and forth to the section of your interest. With that, let's get started. The problem states that you are given a zero-indexed array heights of positive integers, where height psi represents the height of the ith building. A person standing on building I can jump to any other building j if I less than j and heights of I is less than heights of j. So notice a person can jump only rightwards and only to the building whose height is greater than the height of the current building where he or she is standing at. So you are given some queries. Each query will be of the form AI, BI, which means Alice is standing at building AI and Bob is standing at building BI. You need to figure out the leftmost index where Alice and Bob can meet. So if they both can't meet for a particular query, you just return -1 for that particular query. So let's take an example. Let's say we have 6 buildings, each of these with this particular heights, and we have 5 queries. In the first query 0, 1, it means Alice is standing at building 0, Bob is standing at building 1. Now notice Alice can jump to building 2 because it is on the right side, so I is less than j, and also height of I is less than height of j. So Alice can jump from here to here, and in the same fashion Bob can also jump from here to here because of the same reasons. So Alice and Bob both can meet at index 2, and hence index 2 is the answer. They can't meet anything at any index before index 2, so index 2 is the result. Let's take one more example, 2, 4. So Alice is standing at building 2, Bob is standing at building 4. Now notice that Alice can only move rightwards because that's what the condition is. So in the right side there is no building which has greater height than 8. Because of this, Alice can't move at all. Alice needs to stay at current building no matter what. Now similarly, Bob is at building 4, which has height of 2. Bob can move rightwards, but we are sure that Alice can't go to any of the buildings. So Bob, only choice remain is to Bob to go to Alice, but it is not allowed because Bob can only make a jump to buildings which are on the right. So Bob can't also go to Alice. So hence for this particular query, Alice and Bob can't meet, and hence the answer here is -1. So hope the problem statement is clear. Now how to solve this? Let's say we have these 10 buildings and we have some queries. First query is 1, 2. Alice is standing at building 1, Bob is standing at building 2, and second query is 2, 4. Now let's talk about the first query where Alice is standing at building 1 and Bob is standing at building 2, right? So in this case you can see Alice can simply go to Bob, right? Because Alice is at building 1 and Alice can jump to any buildings on the right if the height is greater. So Alice can jump from this to this building, and Bob don't have to move anywhere, and this is the leftmost building where they can meet, and hence the answer for this particular query would be 2. That is, they can meet at building index 2. Now Let's talk about the second query where Alice is at index 2 and Bob is at index 4, right? So in this case, notice that first of all Bob can't go backward. So this Alice is the only person who can go forward to Bob, but in this case it is not possible because Alice is standing at index 2 whose height is 5. So she can't go to building 4 whose height is 4. So this index 4 is not possible for them to meet. Now where they can meet? They can meet at any index after 4 if their height is greater than the height of the building where Alice is standing and greater than the height of the building where Bob is standing, right? So Alice can only jump to buildings of height greater than 5. Similarly, Bob can only jump to buildings of height greater than 4. So for them to meet at a particular building, that building should have height greater than both 5 and 4. In other words, that building should have height greater than 5. So in this case, we have two such buildings and we want the leftmost one, so 7 will be the answer, right? So what we observed that the answer for any query will be either it will be the index B itself, given that Alice can jump there, or it will be the index after B whose value or whose height is greater than the maximum of the two heights where Alice and Bob are standing, right? So that's what we need to find. The first index whose height is greater than a particular value x, and we know x will be equals to max of a comma b, or height of a comma height of b. So that's the problem. If you haven't get to this part yet, I would encourage you to pause now and try to solve this by yourself, or at least give it a try. So we need to find the first index which is greater than x in this particular range. What is the brute force solution? Brute force solution is simply just iterate over the indexes one by one and see which is the first index which is greater than x. So in this case x is 5, let's say, so we will simply iterate rightwards and we will get to 7, and 7 will be the first index which is greater than 5, and hence 7 will be our answer. What is the time complexity of this entire brute force solution? What we are doing, we are iterating over all the indexes in the right one by one. Now how many indexes can be there in the right? Total n indexes can be there in worst case. Let's say a is this and b is this, right? So they have to meet here because everything else is smaller. So in that case you have to go all the way to the last index. So in total you will be visiting n indexes in worst case, and you have to do it for all the q number of queries. Hence the complexity is order q into n, which surely will not pass because number of queries we have is 5 into 10 power 4, and the value of n or number of buildings is also 5 into 10 to the power 4. So this solution will not work for sure. We need to optimize this. So how will you optimize this? Notice we are doing a linear search. So the first thing that you should always try in this kind of scenario is whether binary search is applicable or not, right? So what binary search is, or when it is applicable, I assume you know binary search. If you don't know, I already have a video. I will link somewhere in the top right section or description down below. You can watch that and come back to this video. So you are given some indexes, right, or some sample space. You need to figure out or search a particular index. In this case we need to search the first index which is greater than a particular value x. So in this case this will be the first index in the sample space, second index in the sample space, third value in the sample space, and so on and so forth. So we need to figure out which one of these is the first index which satisfies the criteria. So we divide entire sample space in the half, and if we are able to deterministically say that we can either skip the left half or skip the right half completely, then we can apply binary search, right? So in this particular case, what will be the criteria? We are going left. Let's say we are at index I. Now what is the criteria in which I will say that I am sure answer doesn't exist in the left half? So we want a index which is greater than x. So if the maximum in this range is smaller than x, then I am very sure the answer doesn't lie in the left half, and I can simply skip the left half and only search in the right half. Similarly, if the maximum in the left half is greater than x, it means there is at least one index, one value which is greater than x. That's why maximum was greater than x. So we can safely skip the right half and only search in the left one. Why? Because we want the leftmost index. So even if there are indexes in the right which are greater than x, I don't care. I am sure that I will be finding my index in the left half, so I will only search in the left half. So because you can deterministically say whether to go left or right at every index, binary search is applicable here. So what you are doing, at every index you are either going left or right, and hence your complexity will now become log n. In other words, previously you were visiting all the n indexes, now you will be visiting log n number of indexes, and you will be doing it for all the q queries. So the complexity is now q log n. But there is a catch. The catch is we have to figure out, like, for this log n to successful, or in other words, for us to say whether to go left or right, notice we need to answer the fact which one or what is the maximum element in this range, and this part you can't answer in order one time. If you are able to answer this order one time, this log n is fine, but because you are not able to answer this in order one time, this will be multiplied with the time it takes to find out the maximum element in a range. Now finding out the maximum element in a range can be something you can do efficiently using range data structures. One of them is segment trees. I already have a complete segment tree series starting from very beginning, very scratch, all the way to persistent segment tree and lazy propagation. So if you are not aware of segment trees, you can watch that particular series. I will link that in the description and in the top right section, and I'm very sure you'll be able to understand what segment tree is and how and where to use it. So you can use that here to actually figure out the maximum in a particular range in log n time. So it will be multiplied with extra log n because of that. So how would the pseudocode look like? The pseudocode would be something like this. So I have intentionally skipped the initial parts because I want you to figure out that and code that. We already discussed this in the video at the very beginning. So we are doing searches. So this part will tell you whether B is the answer or not. If B is not the answer, we are basically searching in the range B to n minus 1. So what we are doing, we are figuring out the maximum in the range B to m. If the maximum in the range B to m is greater than the height of the B, so I am assuming that always B will be greater. So in this case, A has greater height, but if A is greater height, you can just swap them. It will still be the same. So the assumption now here is that B always have greater height. So we are simply checking if max in the range B to m is greater than the value at B. If it is, we know that at least one index is there in the left which is greater, so we just simply search in the left half, that is in the range L to M. If that's not the case, we know that there is no point searching in the left, and we will only search in the right half, that is M plus 1 to R. So after this entire thing ends, we will be landing at some particular index L. Now if that is still less, it means there is no index at all in the given array. If it is not less, then L is the index which we are looking for, right? Now let's look at the time complexity one more time from this pseudocode. Notice this while loop. This is the usual binary search while loop, which will be getting iterated over log n number of times, right? Now what we are doing inside this loop, we are doing a max in a particular range, and that we know that takes log n time, so this will be multiplied by log n as well. So this is the complexity. Log n square is the complexity for a single query, and we have q number of queries, so the complexity is q log square n, which is fine for the given time constraint. So if you have watched this point, I would encourage you to pause and try to code this entire thing by yourself. You don't know about segment trees should not be a excuse to not coding this, because I have actually coded the entire segment tree. You can simply copy paste this structure and try to code the rest of the things by yourself. So hope you have at least tried it. Let's look at the code. The code is straightforward. We first build the segment trees, right? Building segment tree we have discussed multiple times, so I'm skipping that. After that we are iterating over each of the queries. For each query we make sure that always B is greater, so we don't know whether Alice meets Bob's or Bob meets Alice. We don't care, we just have to make them meet at a particular index. So we just simply check which one is greater. If B is not greater, I will make B greater so that I can avoid extra if else here. You can simply skip this as well, and you will see there are some extra if else that you need to apply below. So this is a standard technique to make sure that extra if else's can be avoided in the implementation. Now we know index B is always greater, right? So we will simply check if A is B, that is they both are at the same index, or index the one which is at the lower index, the height of that building is less than the height of the building of the greater index. If it is, we can say that the one which is standing at an index A can jump to the building B, and they both can meet at building B itself. So the answer for this case will be B. If that's not the case, we have to figure out the first index after B which is greater than, or whose value is greater than this, right? Now based on this we will do binary search as we discussed in this range B to L minus 1, and we'll see whether to go left and right based on what is the maximum in the range B to M. If the maximum is greater than what we are looking for, we will search in the left, otherwise we will search in the right, and finally we'll be landing at a particular index L. We'll see if that L still not satisfy the criteria. If that's the case, we will simply return -1, otherwise we know L is the one which we are looking for. So hope this illustration makes sense. If you have any doubts in any of the pieces till now, feel free to post them in the comment section below. I would be happy to answer. Next, let's look at a interesting follow-up. Instead of leftmost index, let's say the problem asks us to find out the rightmost index where they can meet. So remember leftmost, the only difference in the follow-up is instead of leftmost we have rightmost, right? Now how will you solve this? So notice what will change. We were searching in the right in the range B to M, right? First of all, what is the brute force solution? Brute force solution would still be the same. Let's say Alice is standing at this position and Bob is standing at Alice is standing at this position and Bob is standing at this position. So instead of now starting your journey from 5, you will now start your journey from 9. You will say, okay, I will start from here. I will look for the first index which is greater than the maximum of this and this, which is 4 and 5, which is 5. So is 2 greater than 5? No. Is 8 greater than 5? Answer is yes. So 8 will be my answer. Previously the answer was 7, but now 8 will be the answer. That's the only difference in the follow-up problem. Now how will you, like, obviously you can see the same thing. Instead of doing a linear search, you can try binary search. Now in binary search, let's say you are landing at this particular index and you need to figure out whether to go left or right. So what will be the criteria now? Now you will say, okay, what will be the maximum in this range, right? Because you are interested in the rightmost index, not the leftmost index. You will check now in the rightmost part first. Is the maximum greater than what I am looking for? If yes, I will go in the right. Otherwise, I will go in the left part, right? So still you can deterministically say whether to go left and right. So binary search is still applicable here. So you can simply have this exact same algorithm. Only difference here would be, instead of searching for maximum in B comma M, in other words in the left part, you will be searching for maximum in the right part first. In other words, you will search somewhere in M comma n minus 1 or n, whatever you say, right? So you will be searching for maximum in this range, and based on that you will take the decision whether to go left or right. Now look closely here. What is variable in this max of m comma n? The only variable thing is now m. N is always constant. So do you need segmentary here? I would encourage you to pause and try to think about this for at least 5 minutes by yourself. So hope you at least tried it. So we don't need segmentary here because L and R is not something varying with every query. Every query we are sure that R is fixed, which is n. So you can simply use suffix maximum and you will be able to answer this in just order one time instead of order log n, and this entire thing will simply run in order log n time, making the complexity q log n instead of q log square n. So just to show this again, so let's say what will happen in the previous case. Let's say you are at this particular index, Bob is at this particular index. So what you will do, you will simply try to find the maximum from B to a particular index I. So what you need maximum in this particular range. So if you maintained a prefix sum there, you need to maintain a prefix sum starting from this index, and the prefix sum would look something like this. Sorry, prefix max would look something like this. But let's say B is not this and instead B is this. If that's the case, notice the entire prefix maximum array has changed completely, right? So with just one variation, the prefix maximum array completely is changing. And if you have to utilize the prefix maximum array, you need to keep this array for every starting point, and that's something which is tedious. That will take order n square time, and that's why we can't avoid using a segment tree here or a range query tester here, right? But in this rightmost case, we don't have this issue, because every time what will happen is you will always say what is the maximum in the range I to n. This is, let's say, I. You will always ask what is the maximum in the range I to n. Now so I can be anything. Now you can say I is not this, instead I is this. Even then this suffix sum will, since this suffix maximum will still be valid, you can simply say the maximum in the range I to n is still 8. Now because R is fixed, you are able to do this. Similarly, in the previous case, if L was fixed, let's say, you will be able to do this. So hope you understand why segment tree was required previously and why you can solve this problem, the rightmost index, finding out the rightmost index without segment tree. If you have any doubts in the piece, feel free to follow up in the comment section below. I would be happy to answer. If you like the video, give a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.